All right, we appear to be live now. Welcome to this good afternoon. Welcome to this edition of Live from Noir Lab at Kitt Peak. I am your host, Rob Sparks, with our moderator, Jamaica Marshall. Our guest today is Stephanie Junot of Noir Lab. Stephanie will tell us about her research into giant black holes and their eating habits. And I'm very excited to hear about that because it's a fascinating topic. Remember, if you have any questions or comments, please type them into the chat and Jamaica will get to them. First, I'd like to tell you about Kitt Peak. Kitt Peak National Observatory is funded by the National Science Foundation and is a NOIR lab facility. It was founded in 1958 and is located about 55 miles southwest of Tucson, located on land leased from the Tohono O'odham Nation. We are indebted to them for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 optical telescopes and 2 radio telescopes. Now I'd like to just do a quick news item. The celestial snapshot captures the majesty of spiral galaxy Messier 106, also known as M106, or NGC 4258. This image is arguably the best yet captured of the entire galaxy. It's obtained using the Nicholas U. Mayle 4-meter telescope at Kitt Peak National Observatory. This image shows not only the glowing spiral wisps of gas and dust lanes at the core of the galaxy, but also leisurely twisting bands of stars around its outer edges. M106 is a popular target for amateur astronomers and can be spotted with a small telescope. M106 is similar in size and luminosity to our galactic neighbor, the Andromeda Galaxy, but lies 10 times farther away, more than 20 million light years from Earth. Though the galaxy measures more than 130,000 light years from edge to edge, the vast distance between it and the Milky Way renders M106 minuscule when viewed from here. Its size in the night sky, if you were able to see it naked eye, is less than that of a penny held at arm's length. For more information, you can see the recent NOIR Lab press release on M106. Now I'd like to get to our talk for today. Stephanie Junot is an associate astronomer at NSF's National Optical Infrared Astronomy Research Laboratory, also known as NSF's NOIR Lab, and a scientist for the Astro Data Lab. She obtained her Bachelor of Science and Master of Science in Physics from the University of Montreal in Quebec, Canada, and her PhD in astronomy from the University of Arizona. Dr. Junot's expertise lies primarily in the field of supermassive black holes and galaxy evolution, but her work increasingly takes place at the crossroads between astronomy and data science. Using telescopes on mountaintops such as Kitt Peak observatories is one of her favorite parts of her job. Besides astronomy, she enjoys exploring outdoors, rock climbing, hiking, and visual arts. Good evening, Stephanie. How are you doing today?
Hi, good. Thank you, Rob. Good to see you.
Okay, well, I will turn it over to you at this point and let you tell us about giant black holes and their eating habits.
All right, sounds great. Thanks. And thanks for being here right now. So let me share my screen and start this. Okay, so I'm actually very happy to be here because giant black holes happen to be my favorite topic. And so what I want to do today is tell you a little about what black holes are. So we'll start from the basic. I'll get on the same page. And then tell you about what we know so far and also some recent work I've been working on as part of my research at NOIR Lab. Okay, so starting from the beginning, what is a black hole? So the name is actually harder to imagine, but a black hole is definitely not a hole. It's in fact an object, so an astronomical object. And the most striking feature is its gravity. So a black hole is an object with a mass, and the mass is what acts as at having this gravitational force. So there's no light that's emitted directly from the black hole itself, so from the object itself. There might be light just around it, just outside of it. This will be outside what is called the event horizon. But because there's no light coming from the black hole, that's why it looks black to us. So there's no source of light there. So it seems to be black, but it's an object. And what we know for sure is that it has a mass. And there's different kinds of black holes. And today, I really want to focus on giant black holes. So what does it mean? So of course, giant, you might already imagine now that I'm talking about bigger ones. But how big, how massive, what does giant mean in this context? So I'm going to give an example that's basically the closest to home example of a giant black hole. And this is looking at the center of our own galaxy, the Milky Way. So the Milky Way is near the center. It's actually very dusty, so it's hard to see. But there is what has been called for a while Sagittarius A star. But what is really there and what can we tell? So there's a couple of different things, right? So because of the dust, we can't really see that well. But what I'm going to show is observations taken over many years of stars, but looking in infrared. So the infrared light helps us to actually see through the dust. So even though if we were to look somehow with like a regular telescope in the center, we wouldn't see much. We would see some stars and clouds of dust and gas. But using infrared observation and really special optics to get the fine details, there's a couple of different groups, and I'm showing the results from one research group from UCLA. And what they've done is looked at the position of some stars that seem to be moving around something that we cannot see. So even with the infrared, they're still moving around something that we cannot see even in infrared. So let me show you here the animation. So this animation is based on real observations of stars. So each dot is a star. They're not actually purple. I'm sure maybe there are purple stars out there. But this really shows how the stars are moving over the course of about 15 years and then it extrapolates in the future. So if you notice, the years now are kind of going in the future. But by tracing the position of the stars over the years, we can see that they're orbiting. We can draw ellipses around their orbits. To draw them, we can actually measure their orbiting. And because we understand quite well the gravity and the laws of physics that are in the orbit, we can actually compute and calculate how much mass the stars are orbiting around. And it turns out that all these stars are orbiting around something that we cannot see, but that something has a mass of about 3 million times the mass of the sun. So that's like putting 3 million suns in one spot. So 3 million suns in one spot will be very, very bright. So that's not just stars or anything like that. So we know it's something very massive, and it's also very small, compact, because the closest star has a very small orbit. So given that there's so much mass in such a small volume, there's no other object than a black hole. So this is what we call a giant black hole, but the technical term actually is supermassive black hole. I think it's debatable whether or not it's more technical than giant. But supermassive black holes, we see that they have masses that range between millions of times the mass of the sun. So the sun itself is already very massive compared to Earth, for example. But supermassive black holes can reach millions to billions the mass of the sun. And the current record holder, I think, is about 10 billion. So that's a lot of mass for one object. Most galaxies have a black hole in their center. So I already mentioned what we're looking at is the black hole at the center of our own galaxy, the Milky Way. But there's hundreds of billions of galaxies out there, possibly trillion. And most of them also have one giant black hole at the center. And actually, I want to highlight the fact that just last year, the Nobel Prize of Physics was awarded to 3 different researchers for the topic of black holes, including Reinhard Genzel and Andrea Ghez. And those are the 2 groups that I mentioned that were both researching the black hole and tracing the stars and their orbit around the center of our own galaxy. So very exciting times. So this is going to be an animation here. So this is an artist illustration just to give a sense of like exactly where is a black hole in a galaxy. So this shows a galaxy here, these nice blue spiral arms, which would be filled with young stars. And then this kind of more yellow center, which has more like old stars. But this is part of a galaxy, maybe similar, not quite identical to the Milky Way galaxy that we live in. So this animation will zoom in. It's basically imagining coming into the center, and there's many stars, and eventually there's this disk of very hot gas and dust that's spinning around something. So the something would be the black hole. So we don't see a black hole here. The black hole would be in the middle of all of this. Okay, so why do we care that there are black holes in galaxies? What do we learn from this? Can we relate to this? So I already mentioned there's probably at least one supermassive black hole per big galaxy center. And they actually seem to relate to each other because it seems that roughly it's a factor of 1 to 1,000. So if I mentioned that the black hole might weigh, let's say, a few million times the mass of the sun, the galaxy around the black hole would be 1,000 times more massive. But there seems to be this kind of special ratio, almost like 1 to 1,000. So it's does this tell us something? Is this a clue? So we think that probably there's some way that the black holes affect the galaxy or the galaxy affect the black hole, or one or the other. But this is still an open question. It's a bit like the chicken and egg question, like which one comes first? Is the black hole coming first and changing the galaxy, or the galaxy coming first and then the black hole grows in proportion? We're not quite sure, but this is a very exciting topic. And this is also a motivation why we're trying to study these objects. And this is also an artist illustration. So you can see the main picture is a galaxy that, and then zooming in, there would be this black hole. And what is illustrated here is a very bright disk of gas and dust, like I mentioned before. So we say that black holes feed on this disk. And we say that because when these disks are happening, imagine like water swirling down the drain in the bathtub, right? It's kind of swirling around the black hole, but it eventually goes to be added to the black hole. So a black hole has a certain mass, but then it keeps getting more and more and more material through this disk. So the black hole is growing. So we say it's feeding and is growing when this phenomenon is happening. We don't always see them or observe them so easily, so we cannot see the black hole itself. But even when there's a bright disk like this, there's extra dust and extra clouds of material, and then you can't even find them, even when they're active, and there's like all stuff going on and swirling around the black holes. Do we have a question?
Hi, Stephanie. Yes, we have several questions from our YouTube audience. The first question is from Mary O'Daniel. Mary asks, do black holes have 1 million times more mass than the sun, or more width than the sun?
Oh, that's a great question. It's really more mass. And in fact, they're not even that much bigger than the sun. So I made a calculation for the Milky Way black hole. I think it was still, compared to the solar system, it would still fit within the orbit of Pluto. So that's very small compared for all the mass. So it's definitely much more dense. So the mass is concentrated into a very small size comparatively.
Okay. And our second question, thank you for that, Stephanie. Mary in the chat, let me know if you have a follow-up for that one. And so our next question, Stephanie, is from Ariel Vallejos. And Ariel asks, what do you think of the Event Horizon Telescope M87 polarization of the ring? Can they provide information about the event horizon or the amount of matter that it ingested?
Okay, so the polarization, so I will show later in this talk the event horizon to the image, but I will not show the polarization. The polarization is telling us about the magnetic fields. And what is going on is the material that's swirling around the black hole. It's not just regular material, it has a magnetic field. So if you think of, I think you might have seen either a magnet or even the Earth magnetic field with these kind of field lines that wrap around. So this material has these lines, but because it's swirling, the field line get entangled. And entanglement, it actually works a bit against gravity. So not all of the gas swirling around will go to the black hole inside the event horizon, because some of this gas gets kind of stuck and even pushed away with the magnetic fields. And in fact, it will take some of that gas away from this bright disk and put it toward these very fast jets. So they call radio jets, and they're basically polar opposite. So if the disk is swirling in one way, like horizontally, the jet would be like vertical opposite to that. So the magnetic field and these polarization results are telling us about how very close to the black hole some material will not go in the event horizon. It will instead take a different course and be ejected.
We appreciate that answer, very detailed and clear. Thank you so much, Stephanie. Ariel, let me know if you have any follow-up questions to that in the chat. And again, to anyone who's just joined us, our guest today, Stephanie Junot, is happy to take questions and comments on black holes throughout the chat. So please post them. Thank you, Stephanie. I'll come back in a little bit.
Okay, great. Okay, so continuing here. This actually is very related to a question we just heard. So I already mentioned black holes themselves are called black because they're light, so it's hard to see them. But we can, however, try to observe what is called shadow silhouette. So if there's a little bit of this bright material around it, we can try to see if possibly we can see this bright material have a certain shape, and that because a black hole makes a shadow. And this is what some of you have seen in the news from last year, but I want to kind of step back and talk about this a little bit, because I think that it's really hard to appreciate how actually impressive the feat was to manage to make these observations. So first step, easy, right? We have to telescope the Earth. So already, to me, that was people even manage this technological feat. But to do this, of course, we can't have one single dish the size of the Earth, right? It doesn't work. But there's a way to have a network of radio telescopes. And if you can see on the image, there's a map here, and that shows yellow dots with the location of the different telescopes. So what happens is that all these radio telescopes pointed at the same place at the exact same time, and they're taking the data together as were one dish, radio telescope. So this has to be done super carefully because the timing has to be exactly the same. So they have to have like atomic clock kind of timing. So to do this, and then to crunch the data took several months, they even had to ship the data on hard disk. And I think from Antarctica, South Pole was a challenge, just shipping this stuff on boat. But eventually they got all the data and they could crunch them to figure out and process them to reconstruct the image that this whole network, which is the size of the Earth, got. But before looking at the real image, the researchers were getting ready. So what are we gonna see? What are we gonna find in the data? So to do this, they have made a very detailed numerical simulations with computers. And you can see on the side here on the right side, this is a simulated image. If you have perfect resolution, which of course no instrument can do this, but this is the kind of thing you expect to see. So the black hole is basically in the center of this image, and then you can see this kind of ring. So this is the material, and the light is amplified differently because of the very strong gravity just around the black hole. And then, ta-da! That was the image. So I remember very well, because when this came, this result came, I was in Australia visiting, and I was trying to watch the press release. I set my alarm. It was in the night, and I kind of slept through it. I missed the live announcement, but I said, okay, fine. I still watch the streaming, and I basically had tears in my eyes when I first saw it, and I was very, very excited. And you can see, then I started to also realize that it was kind of hard to understand. If you don't have a background, it's hard to understand how impressive this is, because people are like, this is it? This is like a blurred orange dot. Like, what's the big deal, right? And I was like, yeah, it's because there's no context. Like, we can't compare it to anything. It's like I know how much we had to zoom in. That's what I do on a daily basis. People don't do this, you know. So what I want to do now is kind of step back, and I want you all to try to have some kind of reference to appreciate how tiny of an image this is, and how much this is impressive that we could possibly even measure this. So to compare to a regular image, most of us are more familiar with, because we see them all the time, right? In the news even, or from NASA, for example. This is the Hubble Space Telescope. Beautiful image. This is a specific galaxy, NGC 2525, Spiral Galaxy. And then this is about 3,600 pixels across. So we're familiar with pixels, right? You take a picture with your cell phone, with your digital camera, each pixel, you know, makes the image. So if we zoom in on a small region, which is this kind of yellow square, it starts to blur because we're really zooming in on this like fewer pixels now. And then if you were to zoom in to just one pixel, then one pixel is just one color. So there's no detail, right, in one pixel. But it's when we have all these pixels, we have this beautiful image. So the reason I'm starting with this is because on the right side, that white square, what is one pixel? And now we're zooming in inside the one pixel to get size of that Event Horizon Telescope edge of the M87 black hole. So by the time you get to here, this is real. This is to scale. This is the image compared to one pixel of this. So I hope now people are starting to appreciate a bit more like how technically difficult this was. So what I did here is I'm showing again, this is the size of 1 pixel of the Hubble Space Telescope image, but Event Horizon Telescope still fits several times in this 0.01, like 1% of a pixel, right? So, and really this emphasizes the fact that we cannot achieve resolution to the details unless the telescope is as big as the Earth, right? Like Hubble telescope is much smaller than the Earth, so we could never see that. So we had to build a telescope the size of the Earth to be able to even resolve this little image of the black hole shadow. So I'm still amazed. And now it's been almost 2 years because it's April 2019. But yeah, it's amazing. So I'm excited that in the future, we should also have more of those images. But in the meantime, we still have many questions about black holes, right? So how do they get so massive? For reasons, how much and how often do they eat? They feed in a star, how do they grow? And also, how do they fit in the big picture? And I would say even in the life of galaxies. So I didn't touch about this too much, but if at the same image I showed before at the bottom, when the disk and jets are happening, there's also these winds, a lot of energy is launched back into the galaxy. So that means is this push the gas, it can heat the gas, and it's made harder for the galaxy to form stars, because to form stars, a galaxy needs to have these clouds of gas, but the clouds of gas, it needs to cool so they can condense. The stars are born in these clouds. But if the gas is pushed, it's too diffuse, it's not going to be able to condense, then the galaxy can no longer form any more new stars. And we also ask questions closer to home. So what about our own supermassive black hole, Milky Way? So right now it's pretty dormant, but is it going to become active again? What would happen? What will we see? There's lots of questions that we can ask. So I would say the basic thing is, how do we find them? Because how do we answer questions if we can't even find them in the first place to study them? So a lot of my work has actually been focused on developing methods and techniques to find the giant black holes, and in particular, find them where they're currently feeding or eating, is what I've been calling them. So otherwise, my cartoon of a black hole, if it's not eating, so it's a black hole, black background, so we can't see it. And of course, and what we can see is either the effect of gravity. So I showed earlier on stars going around, so the orbits of stars. So then we can find the black hole in the middle. But it's even easier when they're eating, because we can't normally see these stars going around in other galaxies. So we can do this in our own galaxy, Milky Way. But if we want to study a lot of galaxies, because we want to understand the story of all galaxies and how the universe took place to come to today, and we really need to study other galaxies as well, and as many as possible. So we need good techniques to find all these black holes and all these galaxies. So when they're in this eating or active phase, oh, I think there's a question.
Oh, sorry, Stephanie. Yes.
No, that's good. Go ahead.
Are you good? Before you went on too much further, I wanted to pop in with questions so they didn't get piled up, so that you didn't have so many at the end, Stephanie. Fascinating. So let's start. We have 4 questions here right now and 4 new questions. So we'll do these 4 and then I'll pop back in a little bit so that you can continue on with how we find the black holes. Okay, so our next one is from Jesus. And Jesus asks, what would be the size, the diameter of the event horizon of the black hole at the center of our Milky Way?
Okay, so so this one, I think it's about, if I remember correctly, and I should probably double check and get in the YouTube comments, but it's at the size of the orbit of Pluto. So it's like within this, it's smaller than the solar system, even though, so I don't have a size in like kilometers, but, or miles, I guess. I can try to pop it back in YouTube later, or maybe if somebody else or Rob can get up, they can also put the size in a different unit.
Sounds good. That's either one of those will work. We can definitely add it in the comments in the video description for sure, Stephanie. Okay, and so our next question is from Phoebe, and this is a question I'm definitely curious to hear your answer on. The question is, do you have a favorite black hole object?
I was not ready for this question, but I do. And I couldn't put it in this talk because I've talked about it so many times now. I do. It's the galaxy is just MG 2582, but the reason it's my favorite, it's because I got these very beautiful data that can map in 3D. The gas is moving around the black hole and it's making these winds, and they like glowing winds. And it's just an amazing thing to study because it allows us to questions about the black hole might be impacting the galaxy, like these winds are impacting the galaxy. So yeah, sorry, I don't have a picture of it in this talk, but I happen to have one, yes.
Oh, that's okay. That's okay. That's great because that's really interesting though. The 3D modeling that you're doing is part of what allows you to see more of the details in that particular galaxy. And that's what makes it so one of your favorites. That's great. Actually, when I saw this question, I thought I had no idea what kind of answer you would give. It was going to be a galaxy, some object that we hadn't even heard of before, or what. So great question. Thank you, Phoebe. Okay, so just 2 more questions, Stephanie, and then we'll let you get back to your talk, and I'll hold the rest of the questions till later. Okay, so Martin asks, he says, Sagittarius A star seems quiet and non-accreting, as you mentioned just earlier. Do we have any observations of older polar jets from it above and below the galactic plane?
Yes, that's a great question. And in fact, we do. So there's a couple of different set observations. Older set of observations with a satellite called Fermi, which would get high energy, I believe, gamma rays. And what they found is what we now call the Fermi bubbles. So if you imagine the galaxies on its side, it's 2 kind of bubble shape, but it's not like full bubbles. It kind of gives the impression of a bubble. It's like 2 rounded kind of shells. And this is very high energy emission. So this would be very hot diffuse leftover gas but then there were arguments about what are the Fermi bubbles from? Do they really come from a black hole, or was there some kind of starburst or something else? And even more recently, there's been new observations with a satellite called eROSITA, which works in the X-rays. And eROSITA found bubbles that are sort of aligned with the bubbles, but at a different size. So now we have basically 2 sets of bubbles to study. And I find it fascinating too. So we can try to trace back. So if we can guess how fast it's expanding, we can try to go back in time and see how long ago these events would have been. So we have to assume, whether they're slowing down or accelerating, but this is how we can indeed learn about previous active episodes of Sagittarius A star.
Thank you so much. And that, yes, a fantastic question. I had wondered as well if we had any data from before on the activity and how the black hole at the center of our galaxy actually acted, maybe 40 or 50 years ago before we had the current data. So it's really good to know that that is there. And just a follow up for me, is that kind of data accessible to the public?
So for the Fermi bubbles and eROSITA bubbles, we did maps that are been published so people can see the images. I am not sure that the eROSITA data are public yet, the X-ray data, because the team is still working. eROSITA is very new, so they're still working on all these results.
Oh, okay.
I will say that this kind of time scale we're talking about can be like hundreds of thousands of years or even millions of years, right? So we're not just going back 50 years where you go. So these are giant bubbles. So they took a long time to get out there.
Amazing, amazing, Stephanie. Yes, blowing our minds. Okay, one last question, and then we'll let you get back to your awesome talk. So this one is from Mark. Mark asks, how long, Stephanie, does it take for a giant black hole to evaporate?
Oh, I don't have a ready-to-go answer. It would be a long time, but I don't actually know a number for this. So for those who are not so familiar, Stephen Hawking explained the process by which black holes evaporate. And that would be, billions of years kind of time scale, but I don't even have a number for sure to say, but it's, so sorry about that. This is something I can try to follow up after.
Sounds good. We appreciate it, Stephanie. You're providing us with so much. I mean, I know my head's kind of exploding with all this new black hole data. All right, I'm gonna pop off of here for now. Keep those questions and comments coming in the chat. Thank you so much. Okay, back to you, Stephanie.
Okay. All right, so I'm going to go back to talking about that it's easier to find black holes when they're what we call active, which means that they're eating or feeding. So this bright disk around. There's also another way that black holes can be eating or temporarily active. So I'm going to show here, this is from a numerical simulation of what happens when a giant black hole eats a star. So just for reference, if you can square, the black hole is located in the center here. Of course, we don't see it because it's just a black hole in the dark. And this, you can see a time scale here. And then there's a star that came really close. So with this close passage, what happens is the gravity is so strong that it's basically tearing the gas envelope of the star. So our sun, right, is like a ball of gas. So if the sun went that close, it's not gonna happen, don't worry. But if the sun were that close to the black hole, it would start to tear the star itself. And it's ejecting in this long trajectory, you get the gas. And some of the gas will orbit and kind of come back around. So this is a pretty long process. The star doesn't just go in the black hole like in 1 second like that. It takes, this is showing what happens after so many days. And eventually this material will keep, and some of which might not make it into black hole, but a bunch of it will go. And then this material gets added onto the black hole. In this case, when it's one star, one event like this, the black hole doesn't grow very much, because if the black hole is already 3 million, then it's like 3,000,001, if this is like the mass of Sun, let's say. So there's other ways. But we say the technical term is the star gets spaghettified as it gets closer, so it's stretched out like a strand of spaghetti. So what I want to then show is compare the different level of activity in black holes. So when they're inactive, so there's nothing happening, they're just sitting there. So it's like a fast, right? You're not eating, there's nothing happening. And then there's a lot of black holes that have a very low level of activity. So let's say a snack size. So the snack size is about 3% of the mass of the sun per year. So this is about how much mass would be accreted through this little disk that as shown in this illustration. A moderately active, which is more common, is maybe the more common among what we consider the actually active black holes. So this is about 1/3 of the mass of the sun per year. So let's say this is a meal size, like kind of a burger kind of thing. And then I was thinking about what's the comparison if a regular active black hole is a burger, what's a quasar? So quasar, you might have heard, is super luminous. They're active black holes also, but they're the brightest extreme end. And this is basically equivalent to eating, in comparison, a food contest. And I was trying to figure out, I think there's a place where it's like 7 pounds of food in one meal with a 4-pound burger. So that's like that. So this is not an everyday meal. So quasars are much more rare, but they're eating a whole bunch at once. And this is equivalent to maybe 4 times the mass of the sun per year. So this is the kind of rates that the different types of black holes are eating. So I'm gonna now talk a little bit about what I've been working on for the last couple of years. And then some of that work is and with a team, right? This is never alone. So big shout out also to graduate student from the U of A, Rega Pucha, has been also crucial to helping with his work here. And the idea is to join different techniques that exist, but combine them together to have a way that we can find more black holes. Because no technique is perfect so far. And we try to find these active black holes, but I already mentioned some complications, right? It's clouds of dust in front. They're buried in there. So there's a lot of difficulties in actually finding them. So the joint technique is, on the one hand, we're using what is called spectroscopy, and I'll say a few more words about how we use that and how it works. So we're combining data from 4 different telescopes. And then, so this is here, this telescope on the left is a Stone Digital Sky Survey telescope, and has a spectrograph. So this takes the spectra. So now we'll see what it means. And then we're using more recent observations. So a big map of the sky with made by a combination of telescopes in Kitt Peak that you already heard about from Rob, and also in Chile. So those are 2 telescopes that are 4 meters across in diameter, and they're mapping the sky over a few years, a few hundreds nights of observations. Combined with WISE satellite, which is in space, and WISE is taking pictures, but with infrared light. So it's like a thermal camera aboard this satellite. So how does that really work? Like, why can I combine these methods, and why do I even want to do that? So the spectroscopy, we can call it making rainbows. So the principle of spectroscopy is just splitting the light into the colors. So if you see a rainbow, is the little droplets. I've split the light of the sun into all the different colors of the white light. So this is the same principle. So we're splitting the light, but we can do more than just looking at colors, because when we split the light of like a star or a galaxy or this gas around black holes, any of these astronomy objects, when we split the light, these very specific signatures, we sometimes call them fingerprints, that we can tell what's in the object that we're looking at. If it's a star, it has these envelopes with hydrogen, gas, and so on. So we can tell about hydrogen, oxygen, neon, because some of the gas, when it's hot, and we call this ionized, it's like the neon signs, right? The neon signs, there's a glass and there's a gas inside. Sometimes neon, but it could be other colors, because neon would be orange. If it's other colors, it would be different. It would be different colors of gas, different color of light. Sorry. So it's like the same principle as this, but basically what happens is this gas around young stars or around these fleeting black holes, we're gonna see it with a spectroscopy. The difficulty, so the advantage is this works pretty well with even these snack-sized black holes. Even a tiny bit of this gas, we'll see this hot ionized gas in the spectroscopy, in the spectra. The problem is, if there's stars and the black hole also at the same time, then we get extra signatures in the spectra of the object. So we do some tricks to separate which ionized gases from the black hole, which ionized gases from the stars. So to do this, this is where the combination is helpful, because this other method is, instead of using spectroscopy, we're also using images. And the way we use these images is we can to look at colors, but we don't just do regular colors. Because regular colors, you can say, okay, blue, red, orange. We actually do a color that also pairs with the infrared light. So infrared light is really thermal emission. So this is a temperature tracer. And what happens is that there's a lot of dust, also dust and gas around the black hole, and the dust gets really hot. So that dust will have a different color in the infrared. So we can look at the infrared and optical, combine all these colors together to say, is there hot dust? And then that's when the trick comes, is to combine it together to say, is there hot ionized gas and hot dust? And then we can be more confident it's a black hole, and it's not because by chance we also have these young stars and or something else hitting the dust that's happening. So that's how, and then in a sense, the novelty is really having this new kind of data-oriented approach and new computer code to combine all the data together and all the combine methods. So I'm going to show the kind of survey and instrument that we're going to use, and I'll dive into the main result, and which is kind of the last part of the talk. So very excitingly, the 4-meter Magle telescope in Kitt Peak, which is on the picture here, has a new instrument now, which is called a dark energy spectroscopic instrument. And this instrument is now being used. So I actually remotely used it from like the spare bedroom for nights recently. There's only two people can be there at the same time on different floors. And then everybody else has to be remotely, but it's still working, which is amazing to me. So we still use the telescope right now. So what this new instrument is doing is that doing this spectroscopy. So it's splitting the light, like I was mentioning before, to split it into the color, or the wavelength is a technical term. But it's doing that for 5,000 objects at once. So how does that work? So this instrument has, there's like a big kind of field of view where it can observe. and it has 5,000 optical fibers, and each fiber is a little robot. So there's 5,000 little robots, and they program with a computer to each go specific position that you right in line with a galaxy in the sky or with a quasar in the sky. And then the light comes in the optical fiber, it goes to the spectrograph, which is what splits the light to the colors of the rainbow. And then we make these measurements, we measure the spectra. So if you do 5,000 at a time, which is the most ever possible, after 5 years of doing this, we'll have 35 million galaxies and quasars. So that's 10 times bigger than the survey I was just telling you about, the SDSS, which is here. So I'm already using this technique, but I'm preparing to applying it to this much bigger DESI project. So it's super exciting. So what's new? And I basically said most of these things in the words already, but we took two methods, one from spectroscopy, one to imaging, and we combined them. And then we compare with independent methods. So I already mentioned like X-ray from EOS. So we compare with X-rays and other methods to make sure that we're really finding active black holes. And when we do these tests so far, we're finding many more, and we're predicting that we're going to find so many more black holes to study galaxy evolution. So I want to show you what that looks like in the sense of what do we find now with the SDSS, and what am I able to predict that we're going to find with the DESI project, which is getting started now. So this is an image of the sky in a small portion of the sky. So there's a scale bar of 5 arc minute here, if some of you know what this means. So the moon by comparison is would fit like 10 times around here. This is already kind of a bigger part of the sky. So what you can see is the green circles show each object that has a spectrum from the SDSS survey. And then of these, so right now there's only 5 in this particular part of the sky. And we're finding from the spectrum and with the infrared colors that one of them has an active black hole. So where I put the little yellow star is like this one we know has a black hole. So for that set of sky, this is how many we're gonna have with DESI. So each green circle will have a spectrum. And of those I'm predicting now, so I don't have for sure the spectrum, but I already have colors in the infrared color. So I'm predicting that all these yellow stars will be where I put the stars are galaxies, objects that have an active black hole in them right now. Or I mean, right now, plus minus some millions of years to us. And if we zoom out, so that image I was showing you before, this rectangle, it's the size, scale is the size of this little green rectangle here. So if you multiply this by 1,000 times, you get this much bigger map of the sky. So this is no longer an image. Each dot here shows a galaxy. So the gray dots are all the galaxies, and the colored in yellow if there's an active black hole. So this is what we have now already, the spectra for from SDSS, and this is what we're gonna get. So you can see that we're gonna get many more galaxies, but to me, even more excitingly, we're gonna get many more active holes. And then you multiply this area again by a factor 150, and this is gonna be the full size of the survey, which is 1/3 of the sky. So you can ask me more questions if you want to know a bit more about the detail of the technique, but to summarize so far what I've told you about, so we know that giant supermassive black holes, well, exist. They have masses between millions to billions of times the mass of the sun. They live in the center of galaxies, and they can eat stars and gas. So this is really the gravity that's attracting. So, and this, if the material gets close enough, the gravity of the black hole dominates, and then the material will spiral in and get added onto the black hole. And working with recent new methods, which is a combination of spectroscopy and images, we find many more active black holes than using each method separately. So this is very exciting. And in fact, so I didn't tell you too much about this, but we don't find just extra black holes that are just snacking. We find some that are having a decent meal. So the ones that are already, like the quasars, are already easier to find. So we don't find so many new quasars. But we find so many more that are just having their regular meal. And that's very important to get the full picture of galaxies And then we're gonna find, a few millions that have spectroscopy with DESI. So with this, we can really answer more of all this question I was asking, like how do black holes grow? How do they relate to galaxies? Do they push the gas and heat the gas in galaxies? Does that affect the lives of galaxies? That's up here. There were some questions, right?
Yes, we do have some more questions and comments in the chat. Stephanie, you really have everyone's brains engaged about black holes. Okay, so it looks like we could use a bit of clarification again on the differences between a black hole and quasar. Here is a question from Phoebe. So Phoebe asks, to clarify, are quasars only quite distant and old compared to closer black holes?
Okay, so quasars, we actually can think of quasar not as an object necessarily. We can think of a quasar, sometimes we call it a quasar phase. A quasar is really when there's a very massive black hole. So typically these are the more massive ones, so towards billion times the mass of the sun. So not just millions, like billions. So suddenly a factor 1,000 here. So these are typically, there's more massive black holes. Because they're more massive, they even have stronger gravity. So when there's material around, this material is like swirling really fast and it's really, really bright. So quasar means that it's a very massive black hole, but it's in this especially active phase. So it's very bright. And what's bright is this disk of material going around. What's interesting with quasar is that they get so bright that the disk can be brighter than all the stars in the galaxy around it. So this means that if there's a galaxy far away and its black hole is in a quasar phase, the quasar might overshine the entire galaxy. So we don't even see the galaxy, we just see a bright point of light. And that's why people start calling them quasars at first too. Another name for quasar is quasi-stellar object, because it looks like a star, but it's not a star, it's just a point of light that's so far away, we just see a point of light. Quasars, there are some that are not far away, that are closer to us. And in this case, sometimes we can see the bright point from the quasar and the galaxy around it at the same time. But quasar is really, we think that a lot of the most massive black holes, like the billion times the mass of the sun ones, they probably had a quasar phase in the past if they don't have one right now. Because quasar is like an eating country, they're eating so much that it's a way to grow a black hole much more effectively. The regular black holes, they kind of grow slower, but the same black hole can have a quasar phase, grow a bunch, and then be quiet. Maybe it has another quasar phase, or maybe it just becomes a regular. So black holes can sometimes be eating, sometimes not. So quasar can be a phase. It could live for some, millions of years or hundreds of millions of years. So the difference, I guess, is black holes are not always a quasar, but quasars always have a black hole in the middle.
That's brilliant. That's perfect. Okay, so, right. So quasars are not, right, that's right. So this quasar phase, I think it makes sense to say that as a phase, because I think it can be confusing, at least for me before, learning more about this, that maybe these are these separate objects, but no. Quasar is just a black hole in its eating phase. And when it's not in the eating phase, we wouldn't call it a quasar, but it's still the same object. That makes sense. That makes so much sense. I hope that answered your question, Phoebe. Certainly send us a follow-up in the chat if not. Stephanie, thank you so much. I don't see any more questions at the moment, but I will say lots of comments. This is exciting. I have so many questions. Thank you so much. This is a great topic. This is a fascinating topic. We've had lots of good comments, Stephanie. So thank you. And just a heads up that we are at 8 minutes till the end of the show.
Okay. So I think that's all I had for the talk. This is another beautiful galaxy here. Let's see. I could, if I may stop sharing and start sharing again, I will show my favorite black hole.
Absolutely. Absolutely.
And for your favorite black hole, I remember several years ago I interviewed you about that for the 365 Days Astronomy podcast. So I put that link in the chat, as well as the press release about it in the chat, so people can read all about that black hole.
Oh, great.
Fantastic, Rob.
And also put a link to our previous live from our lab where we talked about DESI with Parker, so people can get an hour of DESI if they like.
Excellent. And the DESI link is also in the chat.
Okay, let me start. Okay, so I'll just take a couple of minutes if that's okay, and I'll share my screen again. Okay, so I can actually, yes, okay. So what you can see now, so this is this galaxy I was mentioning before. It's NGC 7582. And it's a spiral galaxy. It has a bar. And you can already maybe notice on the scale, there's a right point, like a point of light, very red around here in the center. So I applied for time with an instrument that does what we call 3D spectroscopy. So spectroscopy, remember, is dispersing the light. Instead of just taking one optical fiber and getting one spectrum, this square here has 300 by 300 of spectra. So there's basically a lot of spectra, basically all the points of this image. So it ends up being what we call a data cube. So I'm going backwards here. So instead of one spectrum, we have all the colors of the rainbow, the wavelength, but at each color, we have an image. So we have this red image, we have a green image, a blue image. We can combine all this to get all the light. So this is the white light again. But we can also use this with this of the fingerprints of the elements I was telling you before. So we can separately take an image of just the oxygen, just the hydrogen. So we know which color to choose to get which element. So this 3D spectroscopy or data cube, we can actually have this extra information that we can pull. But also, something I did not mention yet, if this oxygen gas or hydrogen gas, if this is all moving, it will also shift in the colors. So we can actually measure if it's moving. So we can say how fast it's moving toward us, away from us. So there's a bit analogous to the Doppler shift that some of you may have heard about. So to go back to this square, the cube, and I took 3 different colors to make this image. I created this cube, and if we compare it, we can see these dust lanes, and we can see this glow from all the stars. We don't see individual stars, it's just a glow from all the stars. And then it's very red here. So what's going on? So when we looked in more details, this turned out to be this kind of ring, and it's a ring of dust and gas. And inside the ring is where there's an active black hole. So that's interesting. But what else did we learn from this? So we learned that the ring is rotating. So the whole galaxy is rotating. So there's like a motion of the gas. But this ring is rotating even faster. So this is also interesting for us. And this is real data. So this almost looks like an artist's illustration to me, but it's actually in the data cube. I took the green slice where the hot oxygen is, but this is very hot, very ionized. It's doubly ionized oxygen. So it has to be, in case it has to be ionized by this around the black hole. We can see this basically coming out. And it looks like it's coming out. We can measure the velocity of the gas, and it is moving. So it's truly leaking out 2 to 3 meters per second. So that's how fast it's coming out. And it's harder to see, but if you notice at the back, there's actually the same kind of cone shape at the back. It's behind the galaxy. So we see it in between the dust lanes here. So this is what we call a bicone. So there's a front cone and a back cone. So this is the arrows to kind of help you kind of see. So we have from the data, from this 3D data, this gas that's coming out just from this active eating black hole. And to me, to be able to see it, like in the data, like we don't even need to, it's like we barely need to make a model of this, right? We can already see what it looks like and what it's doing. So I find it very amazing. But what also is kind of one of the conclusion of this work is that the ring that's around it is actually protecting the galaxy, because these cones and these winds, they go above and below the ring in some sense, right? So they don't go through the galaxy. They're not pushing the gas and heating gas in the galaxy itself. So I'm gonna stop here again, but that's my favorite black hole.
Thank you for sharing that, Stephanie. And we have two more quick questions in 2 minutes. I will apologize to Martin. I did not see your previous question. So here is his comment and question, Stephanie. And then we have a question from Liz Flemings. Okay, so Martin says, just up here, matter never enters from our time perspective. So when does the event horizon actually expand?
The event horizon, the size of the event horizon is related to that's inside. So it's very hard to think back and forth between the reference frame of something that's falling in versus us being outside. So we're outside of the black hole. Anything that goes within the event horizon, we don't see ever again. But anything that has a mass that goes inside will get added to the mass of the black hole. And there's a mathematical relationship that we can calculate the size of the event horizon as a function of the mass of the black hole. And which also means, so I've talked a lot about black holes eating. I didn't talk at all about black holes merging. But if you have two black holes together, they will merge, they will spiral in and become one more massive and bigger black hole. So the event horizon size, the new event horizon will be the size that corresponds to the total mass. It's not quite total mass because a bit of the mass is lost in the merger, and that can make gravitational waves, which we can detect now that we can detect gravitational waves. Well, I should specify, right now we can only detect gravitational waves from small black holes. In the future, from space with LISA, we should be able to detect gravitational waves from big black holes that merge. So this is something else to look forward to in the future in some years from now.
Very much so, Stephanie. Thank you. And we have a question from Liz Flemings, and she apologizes and says she may have missed this earlier, but what creates black holes?
So in fact, so was this from Liz, you said?
Yes, it's from Liz Flemings from Memphis, Tennessee.
Okay, good. So Liz, if you have missed it, I'm going to say that I've all missed it because this is an open question. So we are studying and trying to understand what we call the black hole seeds. And we're like, so the seeds would be kind of the first black holes that form, and we can use these seeds and grow them. But how does that work? So we have a few different ideas. So we're not completely in the dark, no intended. So we have a few, but we're not sure yet. So black hole seeds could form, you can form individual kind of smaller seeds from stars. So one massive star, and not the sun, like it has to be 100 times the mass of the sun. If that's at the end of its life, it collapses, the core of it might form a black hole. A black hole is at a maximum 100 times the mass of the sun. So that's not enough to have a single seed like this to make then a giant black hole. So there's other options. One option is at the very, very early universe, before there were any stars. One scenario is that maybe the gas can collapse, but not form a star, go directly into a black hole. And that could get a bigger seed. So maybe 1,000 to maybe even 10,000 times the mass of the sun at once. So this is a hypothesis, but we don't have a proof yet that this is happening. And then there's another scenario, it's called a collapse. So imagine if you have a cluster of stars. Some galaxies have a nuclear star cluster, so this could be thousands of stars in the same cluster. And then if at the center there's lots of interactions and things starts to collapse, and then it makes one black hole, but then that black hole attracts with the gravity and all the different dynamics, more and more stars will join. So you basically start to collapse the stars, and then you can build like this also a bigger seed. So second question, we have ideas, but we don't have a for what the seeds of the black holes.
Thank you so much, Stephanie. And I know we're over time. Rob, do we have time for this one last question, or should we wrap it up and have Stephanie answer that in the video description?
That's up to Stephanie. If she wants to answer it, we can go for it.
Yeah, go for it.
Okay, so our last question, thank you, Stephanie. Our last question is from Mary. Mary asks, can one black hole take out material from another black hole? Extract material from another one?
Those are great questions. So if something is already in a black hole and is another black hole, they won't pull the matter, will pull on each other, and they will affect the orbit. And then they will eventually potentially merge. Sometimes you might have a bigger black hole and a smaller, like a stellar mass black hole that comes around, but then the smaller one will spiral in and get added to it. The only time they might share something is they might possibly, if you have two big black holes that are orbiting, they're not yet merged, they're just going probably quite fast, but they might share the same of this hot gas and dust. So, and this sharing a disk, it's thought to be one way to bring them even closer so they eventually merge. So they might share the material from a disk, but they don't steal each other's mass.
Okay, I think that you really clarified that. Yeah, because I was kind of thinking too, if they're close enough, maybe, yeah, the pulling and tugging of materials would happen as well too, but not quite. Okay, and then actually that leads into a question, our last question, yes, for real this time, from, I apologize if I mispronounced your name, Cheme Torres. And Cheme asks, what's the idea or tech needed to detect or see black holes that is still in development or planned to development?
Sorry, can you repeat again that last part?
Yes. What's the idea or tech needed to detect or see black holes that is currently in development or that you know of that's in the planning stages towards development?
Oh, I see. So basically finding proto-black holes in some way. So when black holes are just growing, so there could be some even lower mass of the giant black holes. So eventually we even call them intermediate mass black holes. So these we would find them with the same techniques because they're still black holes and they still have an event horizon and its disk. In terms of like before they become a black hole, to me that goes back to the question of black hole seeds. And in this case, the only thing that is kind of similar to that, I mentioned one of the scenarios is that possibly these nuclear star clusters would form a black hole. So people have been comparing galaxies and they say some galaxies have a nuclear star cluster and no black hole. Some galaxies don't have a nuclear star cluster, or they have very few left, but they have a black hole. So are we catching them before and after? So this is a possibility. It's again, not, there's no like proof yet, but people are actually trying to look for nuclear star cluster as the birthplace of black holes before the black hole form.
Amazing, Stephanie. Thank you so much for answering all of our questions from the YouTube chat. And thank you to everyone in our YouTube audience for joining us today. Thank you so much. And we do have a request for your email address, if that's possible, for further questions, Stephanie. Where can we direct them?
So I'm not sure what you normally do with these requests, but do you give the NOIR Lab or? You can also find me on Twitter.
Okay.
It's Stefa Junot, like S-T-E-P-H-A. Junot, my last name, J-U-N-E-A-U. So that might be a good way if the person wants to find me on Twitter, and I'll be happy to answer questions there too.
Thank you so much, Stephanie. Yes, in the video description, we'll be sure to follow up with you on where you'd like people to send you more questions, including your Twitter account. So thank you so much, everyone in the YouTube audience, for your questions and comments and for joining us. Over to you, Rob.
Yes, I just put Stephanie's Twitter in the chat because I follow her on Twitter, so it was easy for me to find. So thank you very much, Stephanie. That was fantastic. Obviously, the questions from the chat, which were so numerous and intelligent. Show that people are paying attention and interested in the topic. And I know we're over time, but just before we go, Jamika, next week, live from NORLab at Gemini, right?
Yes, next week, live from NORLab at Hawaii, we will be, we'll have 3 guests, and we'll be talking about the development of the Waimea Solar System Walk. Now, this is a community outreach event that all of the Mauna Kea observatories support and contribute to. So tune in next week to find out about that, as well as how to set up your own mini solar system walk wherever you are. Next week, same time, same channel, right here on NORLab YouTube.
Okay, and thank you again, Stephanie, and goodbye, everyone, and we'll see you next week.
Thanks. Bye, everyone.
Bye.